Okay, let's go about naming transition metals. Now, the first thing to ask is why do we need to name transition metals differently than normal compounds? So, for example, why do we have to name NaCl like? Why can we name NaCl like this? Na being alkali metal, but we have to name copper Cl, so copper chloride. My bad. Cu with a 1 over here, Cl. Okay. Roman numeral 1. Why do we have to have two different ways of naming binarity compounds? Well, the reason for that is because the transition metals, they're able to have several different charges. Okay, here I have a periodic chart of the ions, not the elements, but the ions. And you see here that the thing with transition metals is they can have different charges. So, for example, copper can actually exist as copper 2 plus or copper 1 plus. Excuse me. What does that mean? It means that when you find copper, when you say copper chloride, copper chloride, this copper could be either copper 2 plus, so with a plus 2 charge, or copper with a plus 1 charge. We didn't have that when we had sodium chloride. When we said sodium chloride, we knew that sodium always had to be a plus 1, okay? Sodium only exists as a plus 1 charge. That's why you don't see a line in between to separate Na2 plus or Na plus. Sodium can only be a plus 1 charge. And because of that, we can say sodium chloride. Because we know that sodium only has a plus 1 charge. But when we say copper chloride, we don't know that because copper can be a plus 2 charge or a plus 1 charge. What does that mean? Well, if it's a copper 2 plus charge, it's 2 plus, then you would have this compound, right? You have two, because this is a plus 2 charge, you have to have two negative 1 charges to cancel out the plus 2. So you have CuCl2, copper chloride with 2 chloride ions. But if you had copper 1 plus, so copper plus, just, this ion here, then we just have CuCl. Okay, you would have 1 chloride for every copper, whereas with copper 2 plus, you have 2 chlorides for every copper. And if we just said copper chloride, we wouldn't know which one is which. That is why we have Roman numerals beside a transition metal with several different charges. So, for example, if you wanted to specify copper 2 plus, then we would say Cu, the Roman numeral 2. Oh, let me write that again. Would specify copper, Roman numeral 2, chloride. Okay? So you would have, and this 2 means that the copper has a 2 plus charge, okay? If we had a 1 here, it would have a 1 plus charge, but the Roman numeral 2 is here, so we know it has to have a 2 plus charge. So we know because copper has a 2 plus charge, chloride has a negative 1 charge, and once again, chloride, because it's a halogen, always has a negative 1 charge. You need 2 negative 1 charges to balance out the plus 2 charge, okay? If we said, for example, copper 1 chloride, then we know copper has a 1 plus charge, so it'd be CuCl. Okay, now of course we don't have to do this for every transition metal. For example, let's say, I don't know, rhodium is a transition metal, but we don't need to do it for that because rhodium only exists in a 3 plus form, in a plus 3 form, okay? But for example, iron we would have to have the brackets and the Roman numerals, okay? Let's say iron 3, okay? Because iron can exist as iron 3 or iron 2, but rhodium only exists as rhodium 3 plus, so rhodium 3 essentially. So you only need to do the brackets when you have an element that can have different charges, basically. Okay, let's do some examples. Copper 2 iodide. Okay, so we know it's copper. Copper 2 iodide, and it's a 2, so we know it's this ion. Okay, if you look over here, copper 2 means that the copper has a 2 plus charge, and iodide, it's negative 1, so copper iodide. Okay, iron sulfide. Okay, so we look at iron. Iron is one of those transition metals that have several charges. And by the way, This has to do with the electron configuration of the atom, right? In an earlier video, I talked about how the Lewis structure, the Lewis diagrams, like the electrons orbiting around the nucleus model works fine up until calcium, okay? And the reason it up until calcium because the next one over is a transition metal, it's a scandium, right? And when that happens, then everything gets wonky because something's electrons begin filling at lower orbitals, okay? And by doing that, the valence electrons won't change. The number of valence electrons will fluctuate, right? If you're filling electrons in the lower orbitals, that's not affecting the valence electrons, which is why you don't see, 3, 4, 5, 6, 7, 8 in charge. Okay, so let's resume. Iron sulfide, Fe, and we know it has a 2 plus charge, and sulfide is over here also 2 plus, so FeS. Okay, now if it was Fe3, so if it was iron 3 sulfide, then we would have to do this, right? Because sulfide is -2, this version of iron would be +3, and to balance it, you need, +6 and -6. Okay, gold chloride. Let me find gold. Gold is over here. Gold 3 chloride. So we have AuCl3. Chloride being -1. Silver bromide. You see, silver bromide. Silver doesn't have anything over here because silver only exists as a +1. So we don't have to write the brackets. It's AgBr. Okay. Vanadium. If we count vanadium here, we're looking for the +5, not the +4. So vanadium and nitride is a -3. So this one's a little bit tricky. It's okay because 3 times 5 equals 15. Plus 3 times 5 is +15. And -3 times 5 equals -15 because nitride has a -3 charge and vanadium has a +5 charge. At least this version, okay? Lead sulfide. Lead, it's a special compound because you don't name it alongside gold. You don't see GO as gold. You see AU, and that's because I believe the Latin name, it was auric or something. So they had the AU here, as well as, let's see, lead. Lead is PB. Let me see. Yeah, lead is PB, and it's the one with the 4 charge. Okay, so lead PB, lead sulfide. You need 2 because sulfide is -2, as seen over here, and you need 2 of these to balance the +4 charge. Okay. Yeah. A quick guide to Roman numerals. This is 5. If you had, for example, a 1 before the 5, this is the Roman numeral for 1. It's sort of like 5 minus 1, so equals 4. This is why this is 4. And vice versa, if you had 6, it'd be 5 plus 1. The 1 is on the right side of the V meaning 5. And usually the most you'll go up to dealing with transition metals is 7. Okay, that's pretty much the highest the transition metals charge can go. Okay. Yeah, so this would be 1, 2, 3, 4, 5, 6, 7, and maybe 8. Okay. I don't know if this is 8 though. I'm not sure about that, but these I'm sure about. This is 1 through 6. Okay. 1 through 7. My bad. Okay. Gallium. Gallium should be somewhere. Gallium. Okay. This periodic ion says there's a +1, so I'm just gonna go with this question. If there was a +1, then when you have gallium iodide, right? +1 and -1. Okay. Nickel. Nickel, taking the 3 plus version. You have nickel and Se. So nickel is 3, Se is 2. So you multiply Se by 3, nickel by 2 to get a common multiple of 6. Silver sulfide, same thing, except this time we know sulfide has the 2 minus charge, so Ag has to have 2 because Ag is always +1. Iron oxide, Fe, symbol for iron is Fe, okay? And oxide, but remember there's a +3, this is a -2, as you can see over here. And you can just tell by looking at the group it's in. it's in group 6, so it has to be -2. Okay. Multiply this by 2, multiply this by 3, so the charges cancel. Iron oxide. Okay. Ferric. Okay. This is interesting. I forgot to mention this, but sometimes, I mean, usually we use the Roman numeral way, but another way of naming transition metals with several charges is you have an OUS ending and an IC ending. Okay, so for example, if I said copris, that's copper with a lower charge, and if I said copric, that's copper with a 2+ charge. So this would mean Cu2+, this would mean Cu+. It's not used that often, but it is still around, so I might as well teach you it now. Same thing if you said ferris, that's the lower charge, so that would be 2+, Fe2+. Ferric, that would be Fe3+, that's a higher charge, so in this case it's Fe3+, so you get FeCl3. Okay. Manganese 2, it's a lower charge, so would you get MnF2. Okay. Tin is also one of those weird ones. It's Sn, not Ti or anything like that, and those you just have to memorize. Like I said, it comes from an old language. I'm gonna guess probably Roman or Latin, or maybe those are the same thing. I'm not a history teacher anyways. So tin, and if you remember our polyatomic ions, phosphate is PO4 and it has a 3- charge. This has a +4 charge, so you gotta go 3 here and 4 here to get a common denominator of 12, right? +4 times 3, so for tin it's gonna equal 12, and 4 times -3 for phosphate is gonna equal 12 as well, -12, and they'll balance out to be neutral. Cobalt oxide, final one, you have cobalt oxide, same thing as what we had with iron oxide. They have the same charges, so 3, 2. Okay. Now we'll speed through some examples of naming these. So FeCl3, well, we know Cl is always -1. Okay, it's a halogen. Halogens are always -1, just like how the alkali metals are always +1. Okay, well that means Fe has to be 3+, right? Because the charges have to balance. -1 times 3 is -3, and you have to +3 to equal 0. So you know it's 3+, so you say iron chloride. Okay, I'm going to skip some because the naming it tends to be a little bit easier than writing the formula. V, we have vanadium. We don't know if it's +4 or +5, but we look at oxygen. Oxygen is always -2. We have 5 of those, so -2 times 5 is equal to 10. And vanadium, we have 2 vanadiums, so if 2 vanadiums have to cancel out -10 charge, then each vanadium must have a +5 charge, right? Because +5 times 2 is equal to 10. So we know this is vanadium 5 oxide. Okay. Manganese, well, once again, oxygen is always -2. You can see here it's always -2, and you have 2 of those. So -2 times 2 is equal to 4. You have 1 manganese. Well, you can't have manganese 2+, because that you would require 2 manganese. You have to have manganese 4+. So it would be, when you would write this as manganese 4 oxide. Okay, I apologize for moving into the periodic chart of ions. Yeah, okay, let's go to copper. Copper, we don't know the charge, but we know sulfide is always -2. It's in the same group as oxygen, and therefore it has the same -2. Notice how all of the elements in this group has -2. And in order to balance the -2 charge with 1 copper ion, you need to have +2. So to have copper 2 sulfide. Okay, let's move on to its counterpart. Okay, bromide is -1. It's a halogen. Halogens are always -1, so copper must be +1, right? Copper 1 bromide, because bromide is -1, copper has to balance out that -1 with a +1. Okay, so notice how these two coppers are different. This copper is 2 plus, this copper is 1 plus. Okay, let's do tin fluoride. Okay, we know fluoride is always -1. It's a halogen, and because there's 4 of them, the total charge is -4. We need to balance that -4 to get a neutral atom that's +4. So we know tin is tin 4 fluoride. Okay, and finally, silver iodide. Iodide is always -1, but it doesn't matter because silver is also always +1. So because even though it's a transition metal, we just have to say silver iodide. We don't have to put any brackets, okay? If you put brackets, that's wrong. Okay, now after that, let's move on to naming covalent compounds. Covalent compounds are almost entirely different from transition metals in the sense that covalent compounds, they're not ionic compounds. So transition metals, these things, they're ionic, okay? So they donate electrons. I made a video about that. Covalent compounds, they share electrons, and because of that, they not only have a lot more arrangements, because you can have CO2, CO4. I mean, you can't actually, but it's hypothetical. So, for example, you can have H2O, H2O2. You can have H2. You can have O2. There's so many combinations because they share electrons, right? They don't have to donate electrons. They have less rigidity in terms of structure, and because of that, and because they don't really donate electrons, it's hard to give the IDE ending at the end of elements, right? Because IDE denotes an ion, and they're not really ions. So how can we go about this? Well, to name covalent compounds, it's actually really easy. You look at the first element. So you have, so let's say, let's say I have N2O. Okay, so that's we would name this as dinitrogen monoxide. Okay, one thing to note, you are naming a covalent compound when both of these are nonmetals. Both of the elements are nonmetals. So for example, if I combine nitrogen with bromide, with chloride, with phosphate, if I combine nitrogen with, for example, magnesium, we wouldn't have a covalent compound, we would have an ionic compound. Okay, but that's not the case when it's nonmetal between nonmetals. So basically anything over here, these are nonmetals, and everything else is everything else on the periodic table is a metal. Okay, so when we have 2 nonmetals, we know we're naming them covalently. So the example I use, nitrogen monoxide, dinitrogen monoxide. You first have the first element and the second element. That hasn't changed, except when you're writing the second element, you don't add the IDE. Okay, because like I said, it's not an ion. Okay, and then you look at this number. Whatever this number is, you put the prefix. So for example, if it was 2, you say di. If it was 3, then you say tri nitrogen. If there was 4, you would say tetra nitrogen. Okay, and same with the second one. Because there's only 1 here, the implied 1, then we say monoxide. Oh, my bad. Yes, you do put the IDE. I believe oxygen is the exception. Yeah, for oxygen you do write the IED. So we have dinitrogen monoxide. And the best way to explain this is with some examples. We'll skip these for now because these are sort of exceptions. These are, you can think of them as acids. But let's go to number 3. This is called nitrogen monoxide. Okay, you might be wondering why no mono. Okay, so one exception is that if the first element has only 1 atom, then you don't write the mono. Okay, so if we have CO2, we don't call this monocarbon dioxide. We call this carbon dioxide. Okay, we just drop the mono. Okay, now if it's the second element that only has 1, we still keep it. Okay, so for example, dinitrogen monoxide dinitrogen monoxide. Okay, we still keep the mono if it's the second element, but if it's the first element, we drop it. Okay, so this dinitrogen monoxide, we cover that. Once again, nitrogen monoxide. Okay, this is dinitrogen pentoxide. Okay, we don't say pentaoxide, we say pentoxide. Okay, sulfur dioxide. Okay, because sulfur, there's only one of them here, so we drop the mono and we proceed with dioxide. Okay, carbon tetra bromide. Okay, yeah, so I made a mistake when I talked about how we drop the IDE. I was thinking about something else. You don't drop the IDE. Okay, doing some examples, refresh my memory. You can still keep the IDE. Okay, so you name the first element, the second element, you still have the IDE, except with covalent compounds, you have to have a prefix denoting how many there are. Okay, this is we don't really call this, but if you were named like this would be dicarbon hexa hydrogen. No, we don't really name. Okay, so these compounds, they're organic molecules, so we don't really name them like this method. Okay, so forget these two examples and forget these two examples. Now let's do some from names to compounds. Nitrogen triiodide, N. Because there's nothing here, we assume it's mono. We assume it's only one. Nitrogen triiodide, tri, so 3. Dinitrogen N2 tetroxide, so O4. Sulfur trioxide, tri, tetra. Okay, carbon monoxide, that dangerous thing that kills you. Yes, monoxide. See, so even though we drop the mono on the carbon, and we assume it's one, we have to put the mono on the second element. Dihydrogen, that's H2O, but you always say water. You don't really say dihydrogen monoxide. Hydrogen monobromide. This is yeah, you can name it like this. Usually in the form of a gas, but that's in the form of an acid, but that's okay. Phosphorus trichloride. So phosphorus trichloride. There's 3 chlorides. Okay, and the reason we put the tri here is because you can also have, these are all compounds that exist. Okay, well, maybe not PCl7, but PCl3 exists, so phosphorus trichloride also exists, as well as phosphorus pentachloride. Both of these compounds exist in real life, so you have to differentiate between the two, and that's why we have the prefix. Okay, tricarbon. Once again, this we don't really name it like this, but if you were to name it, you can name it like this. Not really. This is an organic molecule, so you would probably end up calling it, let me think, the methyl butane. I'm not sure, but okay. Just know you don't really name it like this. But if if your teacher wants you to name it like this, name this as a covalent compound, then name it as tricarbon octahydride. Okay, and same with this one. Okay. So that's it for today.